visiting from Perimeter Institute. It's my first time in the Southern Hemisphere, so it's a really great experience for me. So my lectures will be about quantum phases of matter. The title has both pure and mixed states, but I think I was a little bit too ambitious, and I think we'll probably stick with pure quantum phases of matter. And so at least when I was an undergrad, I had no clue what quantum phases of matter are. I think typically undergrad courses might not cover much in this area of research. So I think it's helpful to begin with just a bit of motivation for why we should care about quantum phases of matter. So first of all, forget about phases of matter. What is quantum matter, right? So quantum matter is a very broad, overarching word, 2 words. So basically, it means we're looking at a large quantum system and the phenomena that can emerge from it, right? So yesterday you heard from Dario about quantum computers, right? And this is can be thought of as one form of quantum matter. We're putting together, hopefully, many qubits, many quantum degrees of freedom. We know how each qubit behaves individually. Like, we know how to characterize it. We understand the basic laws of quantum mechanics. And yet, when we allow these qubits to interact with each other, we can have a lot of interesting phenomena that emerges from the whole system, but that's not possible from individual degrees of freedom. And quantum computing, the algorithms that you'll hear about, for example, are examples of this collective phenomena. And similarly, you can have quantum materials. These are, maybe like a rock with many electrons, with many magnetic moments. And again, we understand each electron, each magnetic moment very well. But when we put them together and have them interact in a non-trivial way, we can again get phenomena that's very different from those of the individual degrees of freedom, right? So one big motivation for considering quantum matter at all is the phenomena of emergence. Okay, so as I said, we know each individual degree of freedom well. It's built, for example, out of bosonic degrees of freedom, and yet we'll see examples where the collective phenomena that emerge from the interactions of these degrees of freedom is very different. We can start with bosonic degrees of freedom, have them interact, and give rise to fermionic excitations. We'll hopefully get to that by the end of this course. So one big motivation is emergence. Another possible motivation is that it could actually be practical, right? So some of these phases of matter that we'll encounter in this course, topological order, for example, might actually be useful for serving as a platform for quantum computation. Okay, so the phenomenon is not only interesting, but maybe you could use it for quantum processing. So that's a bit of motivation for quantum matter. Why care about quantum phases of matter? Well, as a physicist, it's useful to have a notion of universality. Right? So, there are many different types of quantum materials out there. You could have systems parameterized, with all sorts of parameters. You have like a continuous family of quantum systems out there, and we don't want to go one by one and investigate each one of them individually and characterize them and see what happens. Right? We want a notion of a phase of matter that describes many such materials that unifies the description. Right? So, for example, you might have some quantum material that's parameterized by, let's say, to be simple, 2 parameters, P1 and P2. And so you have many examples of these materials out here, but it turns out that many of these materials might be described by the same properties as some representative point in this phase space. So there could be some representative point that captures the physics of all these materials. So that's denoted by all these arrows pointing at these representative points. And so this allows us to kind of define a notion of a phase or an equivalence class of materials, each of which are well described by a single representative point. So we don't have to worry about infinitely many materials. So this is one of the big motivations for thinking about a whole phase of matter as opposed to individual examples. Okay, so that's a very brief motivation for quantum phases of matter. And so for the lectures, my plan is to start out with just some general principles in the first lecture. And then I'll move on to a specific example that illustrates these general principles. This will be called the transverse Ising model. And through this model, we'll see a phenomenon called spontaneous symmetry breaking. So lectures 2 and 3 will focus heavily on just looking at the details of this transverse Ising model. And in lecture 4, we'll focus on a different type of phase of matter called topological order. And again, we'll try to go into detail in this Tor code model, which is a representative of this topological ordered phase. Okay, so the reference I suggested on the Journeys website goes into a lot of detail about Tor code. So I won't have time to go into all the details, so I encourage you to check out the reference here. It also covers a bit of transverse Ising model in not as much detail, but in any case, it's useful. However, I should warn you that I think the convention in this reference is slightly different than mine. I think you might need a Hadamard between X and Z between the reference and this lecture. And as far as exercises, my plan is to just present 3 exercises. One of them will be a pretty simple, just numerical exercise. The second one will be a more involved exercise that allows you to learn about matrix product states. And the third exercise will be much more challenging and is definitely optional. So that's the plan for these lectures and the exercises. Okay, so let's start. So this lecture will be about basically the formalism for understanding quantum phases of matter from the point of view of lattice models. Okay, so what is a lattice model? So yeah, so fortunately, Dario already introduced the basic degrees of freedom yesterday, qubits. So this definitely helps. So for defining a lattice model, we need to define what the Hilbert space is first, right? Okay, so first let's define a Hilbert space. So as the lattice model implies, we'll consider a lattice of degrees of freedom. Let's say finite dimensional degrees of freedom to be simple, and to be concrete, let's just consider qubits. So you have like a grid of qubits, say along a one-dimensional array, for example. And so as we saw yesterday, we can just define the operators for this qubits by the usual Pauli matrices, sigma x, y, z. And for most of these lectures, unless otherwise specified, we'll work in the eigenbasis of the sigma z operator. So this is sometimes called the computational basis. So we'll work in the eigenbasis of sigma z, which, as you know, is this matrix. So sigma z acting on 0 is 0, and acting on 1 gets a minus sign. Okay. And so the Hilbert space of this entire lattice will just be the tensor product of the individual qubits. And so the dimension for n qubits has grows exponentially with n, right? And so this makes it both at the same time challenging to analyze. We have to deal with the exponentially large Hilbert space, but at the same time it becomes much more interesting. Like new phenomena can occur when we have such a big Hilbert space to deal with. Okay, so that's a Hilbert space. And once we define the Hilbert space, we can now define a Hamiltonian. So the Hamiltonian basically tells us how these degrees of freedom, these qubits, are interacting with each other, right? This is what can differ from material to material, right? How are two neighboring magnetic moments interacting with each other, for example? So in the most general form, this Hamiltonian is just the sum over many Hermitian operators. So each HI is a Hermitian operator that acts on the entire Hilbert space. So this is the most general form of a Hamiltonian. However, in most physical systems, we have an additional principle of locality, of spatial locality. So in many of the, for example, the quantum materials we want to describe, you only have interactions between, say, neighboring degrees of freedom. You don't have a most general operator that couples all n degrees of freedom in your crystal, for example. So this principle of locality is extremely important. Basically, these interactions in the Hamiltonian only involve order 1 or finite degrees of freedom that are usually spatially near each other, right? And so usually we don't want to consider this most general form of a Hamiltonian. We want to assume that each term in the Hamiltonian is local, or in other words, it consists mostly of identity operator acting on pretty much all the qubits except say 2 or 3 or 4 at a time. So you might have a non-trivial interaction between qubits, say I and I plus 1, for example. And we'll have identity on all the rest of the qubits. Yeah. Okay, so henceforth, we'll just avoid having to write all these identities, and this type of operator will be denoted just by sigma I alpha and sigma I plus 1 beta. Okay? And this will be called a local operator. Okay, so just as a very simple example, one type of interaction that we'll see shortly is just a nearest neighbor sigma z interaction. So this is an example. You might just have this two-body interaction between, say, two neighboring qubits. And again, just to remind you what this is, you can expand the computational basis of these two qubits in terms of 0, 0, 0, 1, 1, 0, 1, 1. And the sigma z, tensor sigma z, acts as a 4x4 matrix on this 4-dimensional Hilbert space, local Hilbert space. Okay? So locality is a really essential property, both conceptually and practically. So practically, without locality, we would have to deal with these huge 2 to the n by 2 to the n matrices, which is very hard to deal with in general. And with locality, as you'll see in the first exercise, it actually helps you to numerically study these Hamiltonians much more efficiently. Okay. And conceptually, locality is also very important because it actually constrains the properties of the ground states of these Hamiltonians, as we'll see. Locality places severe restrictions on the ground states of these Hamiltonians. Without locality, our ground states would be highly entangled, basically just like random-looking objects in Hilbert space, which have no structure. And locality will heavily constrain the resulting ground states. Okay, so that brings us naturally to the next important aspects of lattice models, which is what is the ground state of the Hamiltonian we wrote down. So just to remind you, the ground state is just the eigenvector of the Hamiltonian with the lowest eigenvector, sorry, with the lowest eigenvalue. Okay. So this is the ground state, and this is the minimum eigenvalue of H. Okay? And the reason why we're interested in the ground state is because we're often interested in a system at very low temperatures, and so the ground state is basically the system at 0 temperature, and we want to know what the properties of the state are. Okay. And again, focusing on the ground state as opposed to some arbitrary eigenstate of the Hamiltonian is again important both practically and conceptually. Again, practically, looking at the ground state or the low-lying states of the Hamiltonian allow for efficient numerical methods. And conceptually, again, the ground state, as opposed to some random eigenstate of the Hamiltonian, they have very nice properties, as we'll see. Okay. Okay, so that's a ground state. That's the main object that we're interested in studying, given a Hamiltonian describing a system. And the next important principle is something we often take for granted. This is just the thermodynamic limit. Okay, so we'll be interested in properties of the ground state when we take the number of qubits in this lattice model to infinity. Okay, and this basically the motivation for doing this goes all the way back to the fact that we want to understand universal properties of a phase of matter. So when you look at different quantum systems, they can differ locally, right? If you look at like observables, they might differ locally from one material to one material. But if you look at long distance properties, you might find that they all kind of behave similarly, right? So basically, quantum phases of matter are characterized by representative states that all have the same long distance properties, right? And so to define the notion of a long distance property, you need to take a very large system size, right? That's what long distance requires. And that's one reason why we need to take n infinity. The other reason is, again, we want to leverage this assumption of locality in our Hamiltonian, right? So we want to look at Hamiltonians involving local interactions, but locality is only well-defined when we take the whole system size to infinity, right? We want to make sure that the number of degrees of freedom interacting with each other stays constant, is some order 1 constant, while we take n to infinity. Okay. So so that's basically a very brief overview of the setup, the lattice models we'll be considering. And so now we want to look at several properties of the ground state. So given a ground state, what exactly do we want to ask about it, right? So the first thing we want to know are basically observables and correlation functions of the ground state. Okay, so we want to compute correlation functions of the ground state. These might be, for example, local observables. Here, O is the local operator. These might be things like connected correlation functions. These tell us whether or not there are long or short range correlations in the system. So these will be, standard observables we can compute once we have the ground state psi 0. So these will be a good starting point for asking about, what phase of matter we're in. Are we in a phase in which there are long range correlations or not? But later, when we get to lecture 4, for example, in the toric code, for topological order, you'll actually see that we cannot characterize the phase with these standard observables. And so there we'll actually need more machinery to identify a topological order or toric code as a distinct phase of matter from a trivial phase. But usually these correlations are a very good starting point for understanding the phase. Okay, another property we'll want to look at is entanglement. So already you got a nice intro to this from Dario yesterday, so I'll be pretty brief here. So as you saw yesterday, entanglement can be a pretty subtle question, right? So you have states that are manifestly not entangled. You have states like a bell pair that are entangled, but then you can also have a big superposition that also is not entangled. It's a direct product of two definite states. And so, so entanglement can be pretty subtle, right? Like it's often hard to identify by eye, given a wave function, if it's entangled or not. So we want some quantitative measure of entanglement, in particular one that doesn't depend on a basis choice for representing the wave function, right? So let me just introduce the important definition of entanglement. So say we have a bipartite pure state psi AB on two qubits A and B. So to ask how entangled psi AB is, we're basically asking how far is it from a product state. Right? A product state like this or like this is not entangled at all. So we want to ask how far is it from a product state. So for that question, it's useful to look at the reduced density matrix. On a subsystem, say the A system. So we can look at the reduced density matrix denoted by rho A, which is defined by tracing out the other qubit B from this state. Okay, so the whole purpose of the reduced density matrix is to be some object defined on A that reproduces all observables on A. Okay, so one can check that when you define rho A in this way, then indeed, if you look at any observable on A that you compute by taking trace rho A OA, this indeed is the expectation of OA in the original pure state. Okay. So this reduced density matrix is like the optimal description of the A system that reproduces all the original observables on the A system. Okay, and so if we had a product state, if we have a product state, say phi A, phi B, then rho A is simply just another pure state, phi A, phi A, right? So basically A and B are completely decoupled, they're independent. So to reproduce any observable on A, it's good enough just to have the pure state on A alone, right? So in the case of a pure state, rho A is a pure state, a definite state, and that means there's no uncertainty about the state of A, right? So it's a definite pure state, there's no uncertainty which state of the system A is in. However, if you have a non-product state or an entangled state, then in general, rho A will be a mixed state. So it won't just be a single pure state, it'll be a mixed state that's an ensemble of pure states. Okay, so there'll be some probability that the state of A is in different pure states. Okay? And so this motivates the definition of entanglement as basically quantifying the amount of uncertainty in this mixed state rho A. Okay? The more entangled A and B, the more uncertainty there is for each party. Okay? The farther from a definite state it is. Okay? So one can quantify the entanglement between A and B by using the von Neumann entanglement entropy. So this is defined as minus trace rho A log rho A. And this precisely quantifies the amount of uncertainty, or how distributed this ensemble of pure states is in rho A. Okay? So for example, again, for a simple product state, rho A is a definite pure state. There's no uncertainty at all. The entanglement is 0, okay, for a product state. On the other hand, for a bell pair, on two parties A and B, it's simple to check that the reduced density matrix is 1/2, 1/2. So basically, the state of A is a maximally mixed state. It has half probability of being in 0 and half probability of being in 1. So the entropy of this mixed state is log 2. And this is as entangled as one can get for 2 qubits. Okay, so that's a extremely fast introduction to quantifying entanglement. Maybe I can pause for any questions if that was too fast. Yeah. Yeah, sorry, right. Good question. So rho A, by log rho A, you can compute this in practice by diagonalizing rho A. So rho A is, again, some Hermitian positive definite matrix. You can diagonalize it, and diagonalizing the density matrix basically represents this mixed state as an ensemble of pure states, where the probabilities are the diagonal entries, and the members of the ensemble are the eigenvectors. And so once you have a diagonal matrix, this becomes clear. Yeah. Any other questions? Okay, great. So this is just basic entanglement definitions. So we'll be interested in the entanglement of ground states of our Hamiltonians, right? So in particular, say we have a one-dimensional system, we'll want to bipartition our system into some subregion A and everything else. Let's say everything else is B. And we'll want to quantify the amount of entanglement between A and everything else. So in other words, given the ground state, size 0, which is a many-body wave function, does the entanglement in A scale with the size of A? Does it scale with the boundary of A? Or does it scale, with some other function? Yeah. Yeah. Sorry. This just the boundary. Yeah, it's a partial. It's boundary of A. So here for 1D, the boundary of A is just points. So this would mean that it doesn't scale at all with the size of A. Okay. Yeah. It would be constant even as you increase the size of A. Yeah. So basically, the scaling of entanglement will be another important property of ground states. So if it scales with the size of A, we say this has volume law entanglement. If it scales with the boundary of A, we say it has area law entanglement. Okay. Okay, so we covered correlations, we covered entanglement, and the last property we'll be interested in is the gap. This will play another very important role. So the gap of the Hamiltonian is defined as follows. So we'll be interested in looking at the energy spectrum. Energy spectrum of H, the Hamiltonian. And so given a particular system size, like say n qubits, we can, in principle, look at the spectrum. There'll be a lot of states. And then you might have some ground state with energy E naught. And the first excited state might have energy E1. And so the gap is just the difference between these two energies. But again, we'll be interested in taking the thermodynamic limit. We want to look at the limit as n goes to infinity. So we'll want to see the behavior of this energy difference as we take n goes to infinity. Okay. So as you take bigger and bigger system size, does this gap approach a constant? Or does it go to 0? If the former, we'll say that it's a gapped Hamiltonian. And if the latter, we'll say it's gapless. Okay, so the two examples we'll see will be defining quantum phases of matter for gapped Hamiltonians. Okay. One can also talk about gapless phases of matter. However, I think much less is known about satisfactory definitions of gapless quantum phases. Okay, so we'll focus on models in which the majority of the phase diagram is gapped, and maybe only at measure 0 points you have a gap closing. Okay, this will become clear as we go into the example. Okay, yeah, any questions on these basic concepts of lattice models? Pretty straightforward. Okay, so let's just jump right into the first example. We'll go into gory detail in this transverse Ising model now. Write a little bigger, yeah, sure, yeah. Oh, okay, yeah. Yeah, my Blackboard technique is pretty terrible, I apologize. Oh, right, yeah. Okay, so let's go straight into one example to see all this formalism at work. So this is called the transverse Ising model. Okay, so let's consider a one-dimensional lattice of qubits. So I have like a ring of qubits, and let's say there are L qubits. And the Hamiltonian for this one-dimensional system involves two pieces. So the first piece is an interaction between neighboring qubits. So basically, for every pair of neighboring qubits, there's like a sigma z interaction. And just to clarify, we'll now, I guess, so in quantum info, it's common to represent Pauli matrices by just z being sigma z. I hope this is clear. And the other part of the Hamiltonian is just a single site operator. So I have sum over x or Pauli x on every site. So as I said, this first term just involves a ferromagnetic interaction between two qubits. So note that there's a minus sign here. So what this interaction does is, for the system to minimize its energy, it wants to make sure that two neighboring qubits are both pointing in the same z direction, both pointing up or both pointing down. Right, so this is a ferromagnetic interaction, and this thing here is just a transverse field. Okay, so this part of the Hamiltonian wants to point every qubit in the positive x direction. That will minimize the energy of this Hamiltonian. Okay. Okay, so we'll put this system on a ring with periodic boundary conditions. And now we'll want to understand the ground state of this Hamiltonian as a function of these parameters J and G. As we tune these parameters, what will happen to the properties of this ground state? And what are the phases of matter in this simple toy model? Okay. So as a simple exercise, just to get some flavor for many-body quantum systems, I think it would be useful to just numerically compute the ground state and its energy, say for this Hamiltonian defined on a lattice of 10 qubits. So you can use both exact diagonalization. You can just implement this Hamiltonian on 10 qubits directly, and then just numerically diagonalize it and look at the lowest eigenstate and its eigenvalue. Or you can use sparse diagonalization. So as I said earlier, locality is important because it allows you to use things like sparse diagonalization that allow you to go to bigger system size. And so if you're more sophisticated, you can try using sparse diagonalization, allowing you to go up to maybe 20 qubits. And you can look at some properties of the ground state, local observables. You can look at the energy. ED, exact diagonalization, or sparse diagonalization are bread and butter techniques in condensed matter quantum physics. So I think it might be a useful exercise. And so you can ask me if you have any questions or need help with this. So that'll at least give you some hands-on experience with a many-body quantum system and the challenges of understanding it, at least computationally. Okay, but now we want a more analytic approach for these lectures, and so let's just continue analyzing this Hamiltonian. Once we're given a Hamiltonian in a lattice model, it's helpful to look at the symmetries of the Hamiltonian. These are very important. So one obvious symmetry is translation symmetry here. So if I go from I to I plus 1, everything looks the same, right? I have, again, uniform interactions throughout, a uniform field throughout. Okay? And there's also an important global Ising symmetry. So this is defined by an operator called P, which is just the product over all sides of X operator. So basically, this symmetry is just flipping all the spins from up to down or from down to up, right? So as you can see, this operator P, it commutes with all the terms in the Hamiltonian, right? So H commutes with P. And indeed, both the ferromagnetic Ising interaction, ZZ, and the transverse field, they don't care about, they don't distinguish up and down, right? Okay, so yeah, so once you have a lattice model, we want to understand the symmetries, and usually the next wise thing to do is to look at extreme limits of the model to get some intuition. Usually things simplify a lot when you look at extreme limits in the parameter space. Okay, so let's look at some. Was there a question? Or sorry. Okay, let's look at extreme limits. So first, let's look at the simpler extreme limit, which is large G. Okay, so if this term dominates, or for simplicity, let's just set this term to 0. So if this term dominates, then as I said, this transverse field wants to polarize all the spins in the plus x direction, right? So basically, the ground state, I guess for infinite G, is just a direct product of every spin pointing in the plus x direction. Yeah. So recall, I guess from yesterday, that this plus is just the superposition of 0 and 1, 0 and 1 being in the z basis, right? So this field just wants to polarize everything in one direction. And this state is called a paramagnet. Because the Ising symmetry is preserved in this state. The state is invariant under global spin flip symmetry, right? So this is just a very simple product state, right? And so all the correlations are trivial. All the correlations are trivial. There's 0 entanglement. And yes. Oh, this is this? Yeah, sorry, I'm not. This is probably. Yeah, I don't even know what the right notation is. It's just a product over all the Pauli X operators. Yeah, maybe she use a tensor product. Yeah, it's a product of the X operators on every side. Yeah, physically just flipping all the spins. No, yeah, I'm not sure what the standard notation is, but I define this symmetry operator, this to be P. Yeah, why did I do that? Yeah, so later we'll see that this actually has to do with a fermion parity of an associated fermionic system. But yeah. Yeah, so P is the symmetry operator here. Okay, so this trivial product state, paramagnetic product state, has no correlations, has no entanglement. And the third thing we want to look at is the gap. Okay. Yeah, so again, the gap is the difference in energy between the ground state and the lowest lying excited state, right? So can anyone tell me what the lowest lying excited state is for when J is 0? So if I just have the G part of the Hamiltonian, what's the lowest excited state above this state? Yeah, very good. So indeed, the excited states are obtained by just flipping one spin into the minus direction. So let me just denote the excited states by applying a Z operator on, say, the ith qubit, which, as you said, will flip the ith qubit to the minus direction. And so here there are L such excited states. You can flip any of the L qubits, and these all have excitation energy 2G, right? So I've paid a cost of going from minus G to plus G when I flip this qubit. Okay, so this is a very simple extreme limit. It's just a product state. There's an energy gap. There's no structure in this large G limit. Okay. Okay, so let's look at the other extreme limit now. So large J. So now let's, for simplicity, set G to 0. Just consider the first piece. And so now the system wants to minimize it wants to optimize this ferromagnetic interaction, right? So it wants to make sure everything is pointing in the same Z direction, right? So one can see that there are two ground states. Okay, so there's the all 0 state, and there's also the all 1 state. All right, in both cases, neighboring spins point together, and so that first term in the Hamiltonian is minimized. So in principle, it's useful to choose a basis for this degeneracy. Okay, so here we say that the ground state is degenerate. There are multiple ground states. Here there are two ground states. And so it's often useful to choose a basis for this degeneracy that preserves the symmetries of the Hamiltonian, right? So recall that if your Hamiltonian has symmetries, or in other words, it commutes with certain operators, then you might recall from quantum mechanics that there's always an eigenbasis that simultaneously diagonalizes all the operators which commute with each other, right? So one can always choose a basis in which that symmetry P is preserved, right? And indeed, it's not too hard to see that if you take a linear combination, I'll call it a GHZ plus, which is just a sum of these two states. And similarly, we can choose GHZ minus. Then these two states are again ground states. You're just taking a linear combination of these ground states, and they're also eigenstates of the symmetry operator P, right? With eigenvalue +1 for P, and with eigenvalue -1 for P. Okay. So let me just write that explicitly. So P acting on GHZ plus or minus gives you plus or minus GHZ. Okay. J large and negative. You mean like anti-ferromagnetic interaction? Yeah, like I think for these purposes it doesn't matter that much. I think one can play a similar game. Yeah. Okay, so when we take this particular linear combination of the states, now we see that these GHZ states actually have long-range correlation. Okay, so yeah, so one can check that if you look at the connected correlation function, which is defined by it's connected correlation function for the Z operators. You can see that this is exactly 1 for any pair of qubits I and j. So no matter how far apart you take I and j, this connected correlate is always 1. And this is because the GHZ state is such that all pairs of qubits are always aligned, right? So this piece is always 1. But this piece is always 0 because the GHZ state involves both all up and all down. And so the net magnetization is always 0, right? So this is always 1 for GHZ, this is always 0. And so this is 1 no matter how far apart I and j are. Yeah. This is just the correlation function of the ground state. So I'm taking expectation value in the GHZ state. Or in other words, I'm always working at 0 temperature in all these lectures. So I'm just looking at properties of the pure ground states only. Yeah. Okay, so this is already something quite different from the other extreme limit. Remember, here we had a trivial product state. Here we have a state with long-range correlations, long-range ferromagnetic correlations. And moreover, one can check that these GHZ states have 1 bit of entanglement when you cut it. Okay, so if I have a GHZ state on the big system, and I again partition it into A and B, then SA is log 2. Okay? So it has 1 bit of entanglement, not a lot of entanglement, but slightly different from the paramagnetic side. And finally, let's look at the third property, the gap. So can anyone tell me what the excited states are above this GHZ state? So again, let's set G to 0 for simplicity. What are the low-lying excited states above this state? 1 qubit is flipped. Yeah, very good. Indeed. So instead of having all 0 plus all 1, one can now, as you said, flip, say, 1 qubit, and then superpose that with the completely flipped counterpart. Okay? And this will now incur an energy cost that's 4J, right? Because now you have, instead of minus J, you have plus J, and then you have 2 pairs. So that's an energy cost of 4J. Okay. However, this is not the only excited state, right? So okay, so first of all, of course, as before, we can flip, different qubits. We can flip this one, this one, this one, this one. However, can someone tell me a slightly different class of excited states? Flipping all. Well, so remember that these GHZ states are invariant under flipping all the qubits. So yeah. So for example, this GHZ plus will just go back to itself if you flip all of them, right? Yeah, I think you're on to the right idea here. Yeah, I think you're on to the right idea. So basically, instead of flipping just one qubit, you can flip a series of qubits, right? So you can flip like say these and have all 0 here, and then again superpose that with the opposite, right? And you can see that this has the same energy cost 4J, right? So the reason is because okay, instead of flipping one qubit, now you're flipping a so-called domain of defects, let's say, right? And the zeros, like within all the zeros and within all the ones, you still optimize the energy. As long as everything's pointing in the same direction, your energy is optimal. However, you only incur energy costs between 0, 1 and 1, 0. Okay, so these are called domain walls. And so here, this is not that much different than this because you just still have 2 domain walls, right? And so each domain wall incurs energy 2J. So if you have 2 domain walls, you always incur energy 4J. So you can create a domain that's arbitrarily big, right? And yeah, as long as you only have 2 domain walls, you pay the same energy cost. Okay. So yeah, so let me just say on the side that this is a particular feature of a one-dimensional system. In higher dimensional system, the physics is quite a bit different. Okay, so it's only in 1D that you pay an energy cost that's proportional to the domain wall size, not the size of the domain. Okay. Actually, sorry. No, I should say it's always true. You pay energy cost proportional to domain wall size. It's only in 1D that the domain wall size is constant. Yeah. Okay. Yeah. Okay. So we see that this large J, or the ferromagnetic side of this model, is much more non-trivial. You have long-range connected correlations. You have these non-trivial excitations in the system now. And so since you're allowed to flip an entire domain, sometimes it's useful to view these domain walls as particle-like excitations, right? So here on this paramagnetic side, flipping one qubit and okay, I think I'm getting ahead of myself, but flipping one qubit and allowing it to move around, you can view that as a particle-like excitation with some energy cost. And similarly, you can view these domain wall or domain excitations as also particle-like excitations. However, note that here there's an extra constraint on the excitations, right? So here, well, on the paramagnetic side, we could just flip one qubit, right, and pay an energy price. Here, we're forced to create 2 domain walls at the same time. Okay, so here, creating the particle-like excitations, one has an additional Z2 or Ising constraint on it that's different from the paramagnetic side. Okay, and so later we'll see some consequences of that. Okay, yeah, I'm pretty much out of time. Let me just make one final comment. So, yeah, so what's often kind of confusing is this choice of basis we have for the two ground states in the ferromagnetic extreme, right? So again, theoretically, it's nice to always respect the symmetries, and that's why we impose the symmetry constraint to pick out GHZ plus and GHZ minus state, right? And I should have mentioned that this GHZ is, it stands for the people that came up with the state. This I think is Green, Horn, Zeilinger. But you might be more familiar with this type of state in what you might have heard of as a Schrodinger cat type state. So these are superpositions of very different classical configurations, right? And you might have also heard that these Schrodinger cat states are extremely unstable, right? This is why we never see a cat that's dead and alive at the same time. They're very unstable because even very small perturbations to the system can collapse the state. And indeed, that's also true for these GHZ states, right? So, for example, if I have if I prepare these GHZ states in the lab and I just have some little magnetic field pointing in the Z direction, then that might favor one of these two configurations, 0 or 1, right? So any little bit of magnetic field in the Z direction will immediately collapse these GHZ states into one state 0 or the other state 1. Okay, it'll measure the system in the Z basis and collapse it into a trivial product state. And so this is why the GHZ states are conceptually nice, because they preserve the symmetry, but yet they're practically unstable. Okay, so from a more physical perspective, it is useful to think of the ground states as 0 and 1. Those are the stable ground states of the system. However, as I said before, these 0 and 1 states, they break the Ising symmetry, right? The Ising symmetry will transform one to the other, right? So this is why the ground state in this ferromagnetic regime is often called spontaneously symmetry broken states, right? So the physically stable states are the ones that break the Ising symmetry of the Hamiltonian, okay? So let me just write that spontaneous symmetry breaking. Okay. Okay, so that concludes basically the extreme limits, and the next lectures will start going away from the extreme limits and try to map out the rest of the phase diagram for this model. Okay, I guess I'll take some questions.
Hey, in some of the lectures you talk about Berry phase.
Berry phase. I was not planning on covering Berry phase. Yeah, so it's an important aspect of topological phases of matter. In the fourth lecture, I'll talk about topological order, which is a different variety of topological phases of matter, but one in which Berry phase is not that important. But if you want, I can give you some references if you're interested. Yeah.
Okay.
So I had a question. So locality is an approximation, right? Physical systems.
Yes, yes.
So suppose you keep the next term or something like that. How does this change the analysis, or does it disappear for some reason, or?
Yeah. Yeah, so at the end of this example, I'll show you how it falls under like a general paradigm of how gapped local systems have certain structure. And as long as the interactions are some order 1 interactions, like say, as opposed to say, long-range interactions that decay with some power law, etc., then these general aspects that I said should be true. Yeah, well, once you have longer-range interactions, then many different things can happen, right? Yeah, but they're stable to say, like, if you have like next nearest neighbor interaction, things like that, like qualitatively, things look similar.
But like these domain walls would break down, right? That argument wouldn't work anymore. So the 4J wouldn't be true anymore if you.
Oh yeah, that's right. Yeah, these comments are specific to this particular model. But more universal notions like the idea of like a finite energy gap remain true even if you have next nearest neighbor, for example. Yeah.
Is it possible to take out or lose the information about a qubit in a steady state, or isn't it possible?
Sorry, I'm not sure I understood the question. So, it's possible to.
If it's possible to lose the information or take out a qubit in a steady state.
It's possible to lose information in the steady state. So, like, what do you mean by steady state?
I mean, like,
here?
take out a qubit. The qubits, the York gradient, that they're yes.
Yeah.
Is it possible to take out a particle or a state?
Wait. Sorry. Are you asking like how to create or destroy this
yes,
excitation?
Yes.
Like physically. If you, Yeah. That's right. So I think the physical operations you can do for the qubit degrees of freedom, like you just need to flip like one qubit here, right? Perhaps you're asking about this thing I said about the domain wall particles having a constraint
Yes,
associated with it.
Yes.
That's yeah. So indeed, the statement is that your physical operations, like say some like neutron scattering in a magnet, can flip the physical qubits, but these create or destroy pairs of domain wall excitations. So the physical excitations, or removing them, they all involve pairs of domain wall excitations, right? But I guess the point is that the domain wall excitations are the ones we should think of as particles or quasi-particles, because again, you can create an arbitrarily large domain and have only two quasi-particles there, right? Yeah.
Hi, two things. First, the gap energy is 4J because we have basically 4 walls, like 1, 2, 3, 4.
You have two walls. You have two walls. Each wall carries energy cost 2J because you go from -J to +J.
That's where
Yeah.
the 2 comes from.
Yeah, it's 2 times 2, yeah.
Second, could you explain again why the mixed state is 0?
Why the, sorry, the mixed state?
No, that equality.
Oh, well, why this one is 0?
Yes, why that one is 0?
Yeah. So I'm looking at expectation value of Z for this type of state, right? So the first term will give you 1, right? But then the second term gives you minus, right?
Oh, right.
Yeah.
Sorry. Thank
Yeah,
you.
yeah. The average magnetization is always 0. Or more, maybe a more elegant way is that this operator Z, it anti-commutes with the Ising symmetry. So that means that for symmetry preserving state, it must take 0 expectation value, right?
Another question. I don't sure we only view the ground state for talk about the phase of FAR.
Sorry, the question is, why do we only look at the ground state, or?
I don't sure why only view or just view the ground state for talk about the phase of matter.
Like, why do we only care about the ground state for phases of matter? Is that the question, or?
No, why only observation the ground state and not the odds of spectrum?
Yeah, I'm not sure I understood.
You want to know why you don't see the excited states? Is that the question?
Yes. Why
Oh,
I
oh,
don't not careful of the excited state and only the ground state?
Yeah. So usually we're interested in the ground state and the low-lying states because we're usually interested in the quantum system at low temperature. That's where the quantumness of the system is most obvious. So if we have like a higher temperature state, usually if you look at observables, other properties like entanglement, the system looks more classical, right? So usually to see quantum effects, we need to go to a very low temperature. That's where the interesting quantum things appear, right? Yeah.
So when here we have like two different phases, right? Like large J and
Yeah. We'll get to that. Yeah.
when change of phase happens, we will see a conformal, like we were talking with Pedro yesterday. Or
Yeah. Indeed. I think you're getting pretty far ahead. Like, yeah. So indeed, we just started at the extreme points here, but as we've already predicted, we're gonna map out not just points, but an entire phase, and then something will happen between these two extreme limits, right? And indeed, there's a lot of beautiful structure, criticality, conformal symmetry, etc.
Okay.
Yeah.
great.
Any other question? Okay, so let's thank Tim again.